It's a pleasure to be here. I know that you're all tired after 2 hours of work, of listening to us. I'll try to be simple in my explanations. So let's start with a simple observation around us. Look around yourself. What you see, any object, anything is around has 3 dimensions: width, length, height. You wouldn't find around materials which are only 1 molecule or 1 atom thick. It's not because you can't see them. Those materials assume not to exist in our universe. And the reason for this is quite simple. In order to create a material out of atoms and molecules, you need temperature to merge those atoms and molecules together. Temperature creates vibrations, and those vibrations destroy the order in low dimensions. For example, on this video, you can see that there are kind of flattish bits of material, but then eventually everything merges into 3-dimensional shape. Very powerful laws of physics forbid 2-dimensional materials or materials which are just 1 atom thick to exist in our universe. Forbidden in nature doesn't mean that we can't trick around and make those materials. So the idea, with benefit of hindsight, is to take a conventional material like, I don't know, cooking salt. You know that it contains rows of atoms and planes of atoms. And you can imagine that you have tiny, tiny tweezers and pull out 1 atomic plane out of this one. Would this material exist in nature? No theorem, no physics law forbids this, because originally this material was grown at very high temperature, melting temperature. And if you cool the material down to our environment, to room temperature, this material may or may not exist. So this is what we have done effectively 15, 20 years ago. We took a piece of graphite, a material which is created at a temperature 3,000, nearly 4,000 centigrades, and pull out an individual plane. We didn't have tweezers. We can't use tweezers for this. How did we do this? Very simple. Beauty is in simplicity. And in this case, we use a simple sticky tape. You attach it to the surface of graphite, pull it out, and what you see on the surface of the tape, there are pieces of graphite. They are black because graphite is a metal. It's non-transparent. But if you look careful enough in a microscope and shine the light from the back of the screen, what you see here are small pieces of graphite which are transparent metal. It tells you that this material is extremely thin. This material here on this picture, probably about 5 atoms thick. But this for us was eureka moment, because we didn't expect such thin material to exist at all. We were looking for thin film of graphites. The fact that it could be few layers or 1 atomic layer thick, it came as a surprise for us and for colleagues around. So we essentially have done this experiment of extraction atomic flame, not by tweezers, but by scotch tape. And this is how graphene looked like 20 years ago. It's a piece of crystal. It's a crystal structure without any defects. And it's only 1 atom thick. and you see it by naked eye. Between me and you, there are billions and billions atoms, and it's transparent. Here we see one atom crystal lattice, which is there. Of course, you can use all powerful techniques at our disposal, like electron microscopy, to see the crystal lattice, to see what it is. And in fact, it's very simple lattice. It's hexagonal lattice, like chicken wire, it's sometimes called, and it's one atom thick, and it contains only carbon atoms. So if it would be that's it, we extracted one atomic plane, it would be curious, it would be nice, but I wouldn't be standing here and I wouldn't receive the Nobel Prize. The Nobel Prize was given for the understanding of the properties of this material. It looks simple, but over 5 years we start looking at the properties of this material, and it turned out that graphene has many superlatives. It's thinnest, it's strongest, it conducts heat and electricity better than copper, it's stronger than diamond, it's completely impermeable to gases and molecules, and so on. The list goes on until today. We find superlatives of this material. What lesson did we learn from this one? That usually you take a small part of something and you expect this small part would reproduce the properties of this parent material. It turned out to be not true. When you extract atomic plane from graphite, which is called graphene, it turned out to be completely different from its parent material. So, in fact, we find out that properties are not different, but also superior in many respects to the parent material. So, I would like to give you 2 examples of properties of graphene. One is fundamental, one is an applied example. The Nobel Prize was given not for graphene, but for elucidating exceptional properties of this material. And most of those properties, 15 years ago, when it was considered, were about electrons inside graphene. So, this is cartoon. It's very complicated. Let me be simple. When we study materials on this planet, in our labs, in what we have materials, electrons inside move relatively slow, at the speed much lower than the speed of light. And this kind of cartoon on your left describes how we describe materials. But if you are astrophysicist, like previous speaker, or if you are a particle physicist, you describe your phenomena in a different way, using this cartoon in the center. They look very different. This is non-relativistic, and this is relativistic physics, with the speed of particles moving close to the speed of light. So where graphene comes into the play? On your right, you see that electrons mimic relativistic physics very closely. And this came as a surprise, but it immediately gave idea. Some experiments are impossible to do in the most powerful accelerators on the planet and deemed not to be possible to do for the next 1,000 years. They can exist only, say, around neutron stars. In graphene, you can study those phenomena. And this is what we have done about 15 years ago, start looking at those phenomena. One of those is called Klein tunneling, the phenomenon known theoretically in particle physics for 70, 80 years. And let me explain again in a cartoon what this phenomenon is. You know, I don't need to explain what happens to your car if you drive it into a wall. We live in our non-relativistic, non-quantum world. But if you live in a world which works according to the laws of quantum physics, you find out that the car can tunnel through. Some of you with the education in exact sciences heard about quantum tunneling. This phenomena is very important, for example, how your semiconductor circuits in mobile phones and computers work and so on. This is quantum world. But in relativistic world, the phenomena are even more weird than tunneling, which is weird enough. In this case, you try to build a barrier of your particles which are inside graphene in our case, or in real world around neutral stars, and however wide or however high the barrier you make, the car living according to the rules of this world will go without noticing this barrier. Everything goes through. This phenomena seems weird, but this phenomena actually explain one of those things why material is so conductive. You try to localize electrons in graphene, and you can't do that. Nothing, they just go through very easily, and this is why it's 1,000 times more conductive than copper. Another example of phenomena which I like to give you is about applied science which is coming from. You know what Philosopher's Stone is? Probably from Harry Potter, but it's not quite that. Philosophers try to create a substance which turns anything into gold. So it's hard. It's impossible in the real world. But in our case, we use electronic waste. There is a lot of this electronic waste around, and there are a lot of important materials, gold, silver, cobalt, nickel, and so on inside, and you would like to extract and recycle this equipment. It's hard to do, but with graphene, it turns out to be possible. What we did here, we dissolved literally what you see on the picture in a strong acid, and then pour this acid through a collection of graphene flakes. If you do the same with graphite, it won't work. With anything else, it won't work. With graphene, you see the video gets yellow. This is gold precipitates on graphene and only on graphene. So you take this graphene, burn literally it's in air, and you get gold. Very simple, very straightforward, and only gold is extracted. Everything else goes through. So it's in sense, it's kind of Philosopher's Stone at long last. This work was done with my colleagues in Shenzhen, and it's mostly Chinese work, but I like to bring it as an example what is possible using graphene. Now, what comes next? Graphene has been more or less studied during the 5 years. We know a lot of properties. And if it would be only graphene, it would be not as interesting as the excitement is now about the bigger area of research. It's already 20 years ago we showed that graphene has many sisters and brothers, other materials which are only one atom or one molecule thick. Over the last 20 years, there are several hundreds of other materials which people know, which are similar to graphene in their thickness and very different from their parent materials. And obviously, there are many people around the world, hundreds and thousands of research groups around the world try to find interesting and potentially useful properties of these different materials. And this is very hot area of research with thousands of papers published in scientific journals every year, what those materials can be useful for. We make even further step forward already 10 years ago. So 10 years ago, our group thought, okay, we'll get those different materials. They can be 1, 2, 3 layers thick, similar to graphene. But you can do more with those materials. You can think of making now out of those two-dimensional materials, real three-dimensional materials, which are designed by you. They do not exist in nature, but you can design and you can do whatever you want out of those planes. And this is not only cartoon. We play this Lego, essentially, game using different kinds of atomically thin materials to create new materials by design. And this is one of those examples already from 10 years ago, where we disassemble materials into individual atomic planes and then assemble them back intelligently into a new material which doesn't exist. It's a very interesting area of research, and many people work on this one called van der Waals material, but you can consider it as a plain Lego on atomic scale. What comes next? What is further than that? People ask me to tell you about potential applications of graphene. I'm very hesitant to do so because I don't have a crystal ball. I'm not a futurist, but still let me give you a broader perspective of what people in academia and in industry think about these materials in terms how this material and other two-dimensional materials can improve our lives. You know, our civilization followed the development of materials. It's not by accident that humanity moved from Stone Age to Bronze Age to Iron Age, and now we're living arguably at the age of plastic and silicon. Those ages comes because those materials were an important step in the development of civilization. What's next? And some people would argue, and I might even agree with those people, that the next stage could be the age of two-dimensional materials. 10 years ago, it was essentially impossible even to speculate about applications. Using this Scotch tape technique, which is very popular around the world in universities, people still mostly use this technique, which I told you, sticky tape, to make their samples, but it's useless for large-scale production. Over the last 20 years, people developed different technique to produce graphene in tons or in square kilometers if necessary. And people obviously publish different papers, speculate about what is possible and what is not possible with graphene. The range of possible application is actually nearly infinite. If it would be a list, it would be thousands and thousands applications people wrote papers about on the basis of graphene and other two-dimensional materials. I don't want to speculate about what's possible in the future. I'll just want to give you an example what already exists these days. 20 years, it's a very short period from graphene jumping from academia into industrial products. Typically it takes 50, 70 years, but these days you can find graphene which cools electronic equipment in all those products. It's a very important property to cool electronics or light emitting LED to lower temperature, you'll find out that graphene improves quality of different kinds of batteries. You'll find graphene in different kinds of paints in order to improve their protective properties. You'll find skis, helmets, flooring, shoes, different kinds of equipment using graphene to cover them to improve properties which is of interest. It's not a revolution, it's kind of evolution. How do we use this material to improve, sometimes by few percent, sometimes by a factor of 2, properties of and quality of already existent products. I can give you further examples like using graphene in making buildings or covering roads and so on, but we need to think also what possible in terms of graphene revolution or two-dimensional revolution. And there is one dream, and I'll give you only one dream too. People are thinking, talking, and working about a revolution in electronics, using maybe not graphene but other two-dimensional materials. You can think about flexible, bendable electronics. This is cartoon, of course, this is not real, but this kind of electronics in principle is possible. So your watch might be transparent next time, and flexible mobile phones can be also a part of the future. Maybe not in 5, but probably in 10 years it becomes a reality. My final slide is more philosophical for young students in this audience. So if you take a pencil and draw a line on the paper, what you see a pencil trace. And this pencil trace consists of pieces of graphite. This is why it's dark, because pencil lead contains graphite inside. If you take a microscope and look carefully enough through the pencil trace, you'll find out that within those pencil trays there are the same pieces of graphene which are 1 atom thick. So literally, graphene was in front of our eyes, under our noses, literally and figuratively speaking, both, for 500 years since we started to use pencils to draw a line. And we didn't know about this material until the beginning of this millennium. We assume that this material doesn't exist. So the message is that there are still a lot of things to be discovered, I hope, and this is one of those strange things which come seemingly out of nowhere, where you do not expect this. So for young people in the audience, they might be inspired to find something new material, some discoveries. Even the wisest men have never thought about this. Thank you very much.